So we were looking at seismic wave evidences of Earth's interior. Whenever there's an earthquake, there's an energy release. So there are electromagnetic waves and mechanical waves. These are not important. Mechanical waves, since they need a medium to transmit, if we study the properties of these waves, we will get to know the properties of the medium. So there are two types of seismic waves basically, which are surface waves and body waves. Surface waves are of two types, Rayleigh waves and Love waves. These are very destructive since they do not travel to the body. These are not important for studying the Earth's interior. Body waves, on the other hand, they travel to the interior, therefore they are important for studying the Earth's interior. We have two types of body waves, P waves and S waves. These are primary waves and secondary waves. These are longitudinal, so the particle motion is parallel to the wave motion. Here the particle motion is perpendicular to the wave motion, hence they are transverse. These are like sound waves, these are like the plucked string of a guitar. So a few properties of the body waves: the velocity depends upon the density and rigidity, so it is a function of both. When they vary, the velocity will also vary. S waves, they cannot travel to the fluids. P waves, they can travel through, but they will slow down. Now we'll look at the behavior of these waves and what can we infer about the interior from that. So at the shallow depths, the velocity is very slow, 4 to 5 kilometer per second. This is because of the upper granitic layer has low density. So these waves are called PG and SG waves. At 30 kilometers depth, we have Conrad discontinuity, which separates the more felsic and less felsic part, hence the density variation. Because density is increasing, the velocity will also increase to 6 to 6.5 kilometer per second. They are called P and S waves, intermediate P and S waves now. At Moho discontinuity, it doesn't have a specific depth because it varies according to the ocean and continental crust. Velocity will suddenly increase to 7.5 to 7.8 kilometers per second. These are called P star and S star waves. There is more discontinuity. Velocity increases because mantle has higher density. At 100 kilometers depth, there is sudden slowdown to 7 to 7.2 kilometer per second. This is because of asthenosphere. Asthenosphere has very low rigidity because it is semi-molten. Though the density increases, because rigidity is very low, the velocity will decrease. Hence, asthenosphere is also called as a low velocity zone. At 350 kilometers depth, uh, asthenosphere ends. Hence, there is a increase in velocity to 9 kilometer per second. Hence, deep mantle is called high velocity zone. At 2800 kilometer depth, S waves will disappear and P will slow down. The velocity is very slow. This shows us that outer core is completely fluid because of the silicon impurities. Since S wave is transverse, it cannot pass to the fluids. If you look at this diagram, here we have the Conrad discontinuity. The S and P waves are slow. At Moho, after the Conrad discontinuity, in velocity increases. After Moho, it increases further. Astheno, they will slow down, hence LVZ. After that, the velocity will increase very much, hence it is called high velocity zone. Later, S wave will disappear because outer core is fluid. Later, the P wave refracts, showing us that inner core is solid. So this is the S shadow zone and this is the P shadow zone. Remember 103 and 143. Because inner core is solid, the P waves will refract, hence this will be the shadow zone for P. Since P and S waves are continuously bending from here to here, we can infer that with depth, density also increases. And the P waves bend at the inner core, therefore we can say that inner core is solid. So these are some fold mountains. So the Archean mountains are Aravalis and we have Eastern Ghats. Proterozoic mountains we have Vindhyas. Caledonian mountains we have Jolene in Norway. Hercynian mountains we have Appalachians, Urals, and the Great Dividing Range in Australia. Tertiary mountains we have Rockies and Andes. Here we have Alps, Pyrenees, Atlas, Caucasus, Himalayas. Coming to continental drift theory, we have some fundamental questions about the Earth, which are: how did Earth form? What created oceans and crust? How did crustal differentiation, that is, why is ocean and continental crust different? Uh, how did the continents come to be where they are at? What factors decided it? What was the nature of the initial crust or the primordial crust? We need to explain the features like volcanoes, islands, earthquakes, and fold mountains. Fold mountains have some special features like they are only unique to Earth, they are not found on other planets. They are very tall and very large. They have marine sediments, interestingly. Some of the earliest theories they mention that continents are permanent and immobile, but this does not explain fold mountains, earthquakes, and volcanoes. Some interesting observations with respect to continents. Francis Bacon and Benjamin Franklin observed that Africa and South America's east and west coast they fit perfectly. This is called jigsaw fit. And Snyder in 1800s he talked about similarity of coalfields in US and Western Europe. So we can see Appalachian mountain coalfields, Newfoundland coalfields, and Pennines mountains in Britain. And Taylor in 1908 he gave one of the earliest interpretations of continental drift. According to him, there were two supercontinents, Laurentian Gondwana land in north and south. In between, there was the massive sea called Tethys. Due to some factors, they both came together and the sediments got pressed up and turned into the east-west Trans-Eurasian mountains. Now we'll look at the ideas and contributions of Alfred Wegener. Alfred Wegener, he was a climatologist. His aim was to discover its past climate history. He studies three things: rocks, fossils, and sediments. Plus, he used the works of the Francis Bacon we have seen here, Snyder we have seen here, and Taylor we have seen here. He has put together all these observations and gave his continental drift hypothesis in 1912.